I'm Hannelore Andries. I'm from the research group of Applied Electrochemistry and Catalysis, or ELCAT. And my talk of today will be about electrochemical gold recovery from electronic waste. To give a context, every year tens of millions of tons of e-waste are generated, or electronic waste. So it was already more than 50 million tons in 2019, and it will probably go up until 75 million tons by 2030. And if this waste is not properly disposed of, it can cause, apart from local environmental pollution, it can also cause greenhouse gas emissions. So, for example, by improper recycling, just burning in open air, you can release CO2. You can also just release products from the equipment in open air. For example, if you just leave waste refrigerators in open air, they will emit their refrigerants. And more indirectly, the continuous need for virgin materials to replace all the electronics that we dispose of. The latter one, however, is also the main driver for recycling because this electronic waste contains precious metals. It can be copper, for example, the most abundant one, but also precious metals such as gold, which is the material of interest in this research. So within this research project, following recycling process flow was proposed. So it starts from printed circuit boards, PCBs, and they undergo a mechanical pretreatment, which is mainly milling and grinding. And then they undergo a first chemical step, and it can consist of leaching with optionally a preceding pre-wash step to already remove some of the base metals that we're less interested in. And then finally, electrowinning is performed, which means that we will reduce the metal ions back into its metallic form on an electrode. And if everything goes well, then you obtain pure gold in the end. So I'm mainly interested in this research in the electrowinning step, so the last step in this process flow. And even though it's a known process already in the mining industry, for example, to apply it to electronic waste has its specific challenges. So the main one is that the quantities of gold are small compared to other metals, mainly copper, but also, for example, iron. And in the current literature, most research is done in a batch setup, whereas for further industrial use, a continuous setup would be interesting to scale up. So the question is what engineering and electrochemical parameters will impact the deposition efficiency of a mixture of gold and base metals in this continuous flow module. To gather experimental data, a reactor was built. So here you can, in the upper part, you can see the different components of the reactor. So it consists mainly of 2 glassy carbon plates, and one of them is a cathode, which is used to deposit the metal on it by reducing it. The liquid is pumped from a feed vessel through the cell and recirculated back. As a starting point, a reference solution is used, which contains of gold, copper, nickel, and iron. This is to really assess the parameters in a reproducible way, since the waste itself is very heterogeneous. So a few parameters were tested. The first one was the potential. So we're in an electrochemical reduction, so normally lower potential should result in higher reduction rates. However, this does not stimulate the gold recovery anymore if we go lower than plus 0.4 versus silver chloride reference. And this is mainly due to the fact that there will also already be competing reactions, which are mainly copper reduction and iron reduction. These will only partially reduce, for example, from iron 3 to iron 2 plus, and they will not go into their metallic form. So we will still have pure gold, but the efficiency of the recovery will decrease. Secondly, also the flow rate was tested. As expected, higher flow rates give higher mass transfer in this continuous flow reactor, so higher recoveries. And then also a solution was tested with only gold to compare between gold or a mixture of gold with other metals. And especially at the lowest potential in the range, the plus 0.3 volt, there you could see again that with gold alone in the solution, the recovery goes faster. So there you can again see clearly the competition of other reactions from copper or iron. And then finally, we also tried to insert turbulence promoters in the system. The idea was to enhance the mass transfer further and that way to also enhance the gold recovery. It did, however, not result in a better gold recovery on average after 4 hours. What it did do was make the different repetitions more reproducible. So see here at the error bars that the standard deviations are much lower. So it makes the system less sensitive, more reproducible. And if you look into it further, you can even see that the deposits are different. So without the turbulence promoters, this left-hand plate here is the actual deposit. The density of the deposit is the highest in the middle and near the edges, and in between there is almost nothing. That's also what you can see in a simulated velocity profile, which is here below. So here in the middle there is a large inlet effect, which gives higher velocities, gives more turbulence, but here in the middle there is almost dead zone. The crystals that are formed, according to the SEM images, they are rough, they are slightly dendritic already. Whereas if you look at the situation with the turbulence promoters, we have a different story. There you see that the actual deposit on the plate is more randomized, more uniform, not at specific places where there is more density. And the velocity profile is also smoother, so that the inlet effect is broken by the turbulence promoter. And the SEM images show that also the structure of the gold crystals are different. So they are smoother. They don't have these sharper structures. So this shows really clearly that even though the average recovery is the same in both cases, there are still structural differences in the process, and it leads to the case without the turbulence promoters being more sensitive to small changes. And also on a larger scale, these rougher crystals could lead to other problems. For example, more high probability of short circuiting, or they can even break off, which has already been reported. So there we see that actually the turbulence promoters are still interesting to insert to enhance the gold recovery on the longer term. So to conclude, the gold recovery can be done up to 86% after 4 hours in continuous mode. Potential needs to be kept high enough to minimize competing reactions, and turbulence promoters mainly generate more consistent recoveries. And as a future perspective, we would like to bridge the gap between the synthetic solutions that have been used up to now and the actual waste solutions, which also means that the pre-treatment steps will be taken into account, and also the presence of other impurities. So thank you for listening, and also thanks to my project partners and my colleagues to make this research happen.